Okay, so the next speaker is Amalia Coldea from Oxford. So she'll be talking about the quench nematic quantum critical points in the software domain. So Amalia, the floor is yours.
Hello, good afternoon, everyone. Good morning to you, and Happy New Year and a better year to all of you. So today I'm going to talk about specific electronic correlations in the vicinity of the putative nematic critical points in the ion selenium sulfur tuned either by pressure with sulfur substitution or by chemical pressure or by applied physical pressure in the 11% ion selenium sulfur. And the Fermi surface of these materials, as we know, they are multiband system, and I'm going to discuss the details from quantum oscillations and the quasi-particle masses. So firstly, let me acknowledge my collaborators, in particular, Pascal Rees and Matthew Bristol from Oxford for their high field magnetic high experiments. I'd like to also acknowledge all our collaborators to high magnetic field facilities, Dave Graff in Tallahassee, Alex in Nijmegen, William in Toulouse. And we couldn't do these experiments without having high quality crystals grown by Amir Shiv and previously by Shigeru in Tokyo. So we've been working in this area since 2014, and we've done lots of studies of RPES to understand electronic structure. But in this talk, I'm going to focus mainly on quantum oscillations, and a recent review about the systems is here. So following on what we learned in the previous talk, obviously a big question in understanding ion-based superconductors, understanding whether magnetic or nematic critical fluctuations are responsible for enhanced superconductivity. So one of the early predictions for a nematic criticality was if we have a tuning parameter, we expect that in the vicinity of a nematic critical point, the resistivity to be non-Fermi liquid and the superconductivity to be enhanced. So that means if we were to probe order parameter, we might expect that the quantum critical point, as we vary a tuning parameter, we should have some divergent fluctuations. And in experiments, quasi-particle effective masses are used to test if these scenarios are valid. So as we heard before, ion selenium sulfur series is an ideal case to search for evidence of nematic criticality and to tune across the phase transition by suppressing nematic phase and search for evidence of any unusual behavior. And as we can see and pointed out by a few of the questions, in the vicinity of the nematic endpoint, superconductivity is not enhanced, but instead we have a small enhancement inside the nematic phase. The phase diagram also shows that for higher doping, superconductivity slowly varies with composition. And for the N-member compound ion sulfur, resistivity versus temperatures here, one can see one recovers Fermi liquid behavior. Whereas inside the nematic phase, this behavior is very complex, as discussed by Nigel as well. And in a high temperature regime, we see the trends towards saturation and bad Fermi, bad metallic behavior. So one of the powerful techniques to search for nematic criticality is to probe the nematic susceptibility of the systems. A nematic susceptibility is the anisotropy in resistivity, the in-plane anisotropy under a small amount of strain. And the study done in Japan showed that for ion selenium sulfur, the nematic susceptibility show Curie-Weiss temperature, and for composition close to 17%, then the intercept Curie-Weiss temperature is close to 0. While Curie-Weiss is a good indication that a potential nematic critical point be present here, this is a mean-free behavior, so it doesn't tell us too much about fluctuations and what happens at the critical, the quantum behavior, low temperature, and what effects this could have on superconductivity. So again, one more point about iron selenium. What we learn is that besides having a nematic electronic order below 89 Kelvin, the system couples also with the lattice. So that means when the system enters the nematic electronic order, the lattice suffers distortion from tetragonal to orthorhombic. From lots of studies of RPEs, we learn also that orbital degrees of freedom play an important role and affects how the Fermi surface distorts, and we see very strong anisotropy as we enter the nematic phase. Furthermore, the electronic correlations, short range, long range, and the effect of spin fluctuations, I think are very important, but this is not I'm going to discuss today. Oh, sorry. So when we discuss about the coupling with the lattice, we have to remember that actually the lattice distortion from tetragonal to orthorhombic corresponds to transverse acoustic phonons. So the distortion takes place along the diagonal of the tetragonal lattice, and these two are the two types of acoustic phonons. And inelastic X-ray scattering, which could probe the acoustic phonon, also show there is a finite nematic correlation length, and suggesting again that this can be described by a mean field theory, which cannot tell us about the nature of fluctuations at low temperatures. And besides using chemical pressure, in this talk, I'm going to also talk about the effect of applied pressure. As we heard earlier, the pressure is a unique parameter combined with chemical pressure in the system allow us to really tune the nematic phase away from spin density wave phases. And in the 11%, we have a regime where there is no spin density wave, so we can easily look into the behavior of this point together with the behavior with the, in the case of the chemical substitution. So for this, we are using quantum oscillations, which is a very powerful probe of Fermi surfaces and of identifying the behavior of quasi-particle effective masses. So in a quantum oscillations experiment, due to lambda quantization, we see oscillations in the density of states, and the frequency of these oscillations will be related to the extremal areas on the Fermi surfaces. So for example, here, in a case of a two-dimensional cylinder, we have a minimum and maximum frequency, and you can imagine that for a multiband system, the frequency spectrum becomes very complex. So quantum oscillations allow access to lots of other parameters, and using the Lifshitz-Koseevich formulas, we can access directly the effective masses, which are cyclotron average in a quantum oscillation experiments. And if somebody can calculate the band masses and estimate the effect of electron-phonon interaction, then directly from the quasi-particle effective masses, one can relate the effect of the strength of electronic correlations. So let's remind ourselves a few aspects of the Fermi surface of iron selenium from our past studies. Well, we learned that the Fermi surfaces are extremely small, and they are so much smaller compared with band structure calculations. So this is a DFT calculated Fermi surfaces having 3 hole bands and 2 electron bands, whereas this will be a Fermi surface in the tetragonal phase, which shows we are only left with the hole band and a small pocket center at the Z point, whereas and the 2 electron bands at the brilliant zone. So these effects are very complex, and there is still a lot of debate what causes all this renormalization and shrinking of the Fermi surfaces. And one of them also touches upon the effect of orbitally dependent renormalization factors of the band structure. Whereas the bands which have XZ or YZ character are renormalized by factor 3. For the bands which have XY character, in particular here, this gamma band, this renormalization can be very large, 8 to 9, and in other chalcodenides can become even larger. So here is an example of how quantum oscillations look like. We measure resistance in applied magnetic field. We need extremely high fields to get over the upper critical fields. And in the normal state, we see quantum oscillations. We Fourier transform this spectrum, and we have a complex spectrum of features. And today I'm going to focus mainly on the highest frequencies. So what we know from RPES that in iron selenium, we have a quasi two-dimensional cylinder, and this will correspond to the orbit delta and beta. So beta is the minimum and delta is the maximum orbit on the cylinder. And the rest of the features will be associated with electron bands. And if we now follow the evolution of the system with chemical pressure, again, there are quantum oscillations across the whole series, but the spectrum of this oscillation changes quite a bit. And probably here it's worth reminding ourselves that we are dealing with a multiband system. So if you measure resistance, then you have to think about a parallel network resistor. So the channel which has the highest conductivity is going to dominate our response. And what we can see in the data, this is the derivative to enhance the frequency spectrum. We can see that around 12%, a very low frequency seems to dominate our spectrum, and this low frequency disappears. While at the same time, we can follow easily the high frequency components. So the delta is the extremal orbit on the whole band, which I'll focus on today. And we can see as a function of chemical pressure, this band position goes to higher and higher frequency. That means this pocket increases in size. I forgot to mention earlier that in iron selenium, the inner hole band as a function of temperature disappears, but with sulfur substitution, it returns back again close to 11%, where we start seeing this pocket. So the fact that a pocket disappears, whereas RPES suggests that it should appear, is rather unexpected. Now let's look at the summary of our findings from quantum oscillations. So there are lots of graphs here. First of all, the full frequency spectrum versus X shows in general an increase in all the pockets. That means that the Fermi surfaces increases, the number of carriers increases, but there is this particular dominant highly mobile carrier which seems to disappear together with nematicity. And this is quite different from, these are the RPES data for the whole pocket, which show this anisotropy between the X and Y direction, and the presence of this additional inner hole band from about 11%, but there is no indication of a disappearance of the pocket. Moreover, here there is slightly zoom out the effect of superconductivity, again showing that at the nematic endpoint, there's rather a drop, and the enhancement which exists is inside the nematic phase. We also measure magnetotransport in 34 Tesla, and this is just a derivative of resistivity in 34 Tesla, which seem to differentiate between the regime below 11%. This is below, we have this three-dimensional hole pocket appearing. So we call this phase nematic phase A, compared with the phase B, where we have this low frequency dominating, which disappears together with nematicity. Now let's look at the effect of applied pressure for the 11%. So this is temperature versus applied pressure. We can nicely suppress nematicity within the same sample. So doing pressure experiments it's a beautiful way to tune phase transition without really changing the sample. So we are dealing with the same material. We do not induce additional degrees of disorder. And you can see here resistivity data show nice smooth behavior. There is no linear resistivity in the vicinity of nematic endpoint, but a possible linear behavior starts setting in as we move towards the spin density wave regime. Now, if we go back to quantum oscillations data, and again, focusing mainly on the highest frequency peak, which is the delta, is the whole band pocket, we can see this increases similarly to the chemical pressure effects, and a similar Lifshitz transition, the disappearance of a dominant low frequency spectra occurs here as well. So there's a very good correspondence between the chemical and applied pressure in the system. Again, the frequency mainly increases in size, the number of carriers increases, whereas one of the pockets seems, which is very mobile, seem to disappear. I'm going to come back to the effective mass in a minute, but you can also see that nematic phases compared with the outside the nematic phase under pressure, this has very low Fermi energies. And here in the tetragonal phase, we increase significantly the Fermi energy as well. So as I said, one effect that quantum oscillations see in addition to what we learned from RCQM data is that we have an unusually dominant low frequency pocket, which disappears together with nematicity. And one potential explanation for this is we have to think about a quasi two-dimensional cylinder. You have two different lattice parameters if you have sulfur or if you have selenium. That means the degree of interlayer warping will increase as we move towards the sulfur end, and potentially we have a topological Lifshitz transition where we lose one of the frequency because the neck of this cylinder disappears. Another possibility is effects caused in magnetic fields. In particular, for the case where you have very small pockets, you expect very strong spin polarization, which could cause some of the observed effects. So now let's concentrate on the quasi-particle effective masses in the vicinity of these nematic endpoints. And these effective masses are extracted from the amplitude versus temperature of the quantum oscillations. If this dependence varies significantly with temperature, that means the effective masses are very heavy. And this is for a 4% concentration deep inside the nematic phase. And this is for a concentration outside the nematic phase. So we can see already that the masses are quite heavy inside the nematic phase, but they become lighter outside in the tetragonal phase. And this is a summary of all our findings for the sulfur substituted system. Now, if we look on the smaller scale, the changes are quite subtle. There is both here, I look at delta, which is the outer hole band, but also we can detect for a certain regime also the gamma pocket, which is supposed to have dxy character, and it's much heavier than the delta pocket. We can see both of them slightly increase, but for higher concentration, we can only follow the delta pocket, and then this goes down again. Now, if I only look at the delta pocket and I add the results by Terashima for iron sulfur, what we can see is now a bigger picture of what really happens to the effective masses is that there is some variation inside the nematic phase with a small peak in the middle of it. But then as we cross the boundary of the nematic endpoint, there is no divergence. The system does not really has a significant enhancement here. And we compare this effective masses with the values of the A parameter measured by us and by Nagel's group. And then we can see that if we add the A parameter, this is on the left side, and the effective mass is on the right side. Once we account for the nominal composition effects that Nigel used in his paper and shift all these points to the left, then we can see that all the data nicely follow a smooth variation, a slight increase towards 10%, and then a decrease as we cross these boundaries. Also from RPES, one can probe different velocities, and they have a smooth variation across the nematic endpoint. And in this graph, I also added the data of all the possible experiments existing on the series which probe the electronic behavior of the system. So we have the effective masses from quantum oscillations, red points. We have the A coefficient from transport data from two types of transport data, and also the gamma coefficient from specific heat data measured by Matsuda's group. This is divided by 2 just to bring them on the same scale. And here you can see that the trends in all this behavior is to have a slight increase before they decrease, and there is no enhancement at the nematic endpoint. And now if we look at the pressure effects, where we were looking for the same signature, and again, we were interested to see if there is an enhancement, so we could follow with quantum oscillations in a single sample the behavior in very much detail, and every time we see the same effects. The effective masses are quite heavy, so it's a quality system inside the nematic phase. They drop smoothly around the transition, and then there's almost like a plateau, maybe slight increase at the higher pressure. So despite the fact the masses are not showing an enhancement, it's probably worth mentioning that the amplitudes seem to be much more suppressed inside the nematic phase compared with what we expect from LK formula. So we think there is additional scattering inside the nematic phase, which probably affect, as we learn, magnetotransport and transport behavior. So here's a summary now of the data under pressure, looking at the effective masses and the A coefficient from the transport. And in both cases, a smooth behavior happens across the nematic endpoint. So the critical pressure is supposed, where the nematic transition is suppressed, is around 6 kilobar. And as you can see, there is no signature of enhancement in both of these quantities. So now thinking about superconductivity, TC is represented by the open triangles here. We can see that there is a very nice correlation between how the quasi-particle masses and TC varies, telling us that whatever caused the changes in the quasi-particle masses also affects superconductivity. Whereas as we go in a higher pressure regime, so now with pressure, we heard that we are moving towards a regime where potentially we go towards a spin density wave, we can see that this correlation is broken. So that suggests that probably the type of superconductivity we discuss in this regime is likely to be different from the type at higher pressure. So here the correlations seem to be weaker. The Fermi surfaces increases, so we expect that the carrier density to be much larger. So TC is likely to be enhanced for having more carriers. And now how this compares with the system where we know that exists a magnetic critical point, the barium-122, that we also heard in the previous talk, we can see that there are striking differences between these two materials. So in barium-122, we have a strong enhancements in the effective masses as they approach the magnetic critical point here, and there is a divergence in the mass. At the same time, there is a linear resistivity happening at the same place, and the superconductivity is enhanced. So I combine in the review paper a graph showing these two systems side by side for easier comparison. And so what we can learn from here? Well, we learned that indeed in the presence of magnetic fluctuations, the effective mass are enhanced approaching this quantum critical point, and TC has a strong enhancement. But in the case of the system where nematic fluctuations are supposed to be in the driving seat, we do not see a mass enhancement, and we do not see an enhanced TC. So this is telling us two things: either that this superconductivity is not caused by nematic fluctuations, or somehow that our nematic fluctuations are shifted in a different position. So you can see here that there is a clear correlation between TC and effective masses, but it's inside the nematic phase where we know spin fluctuations might be stronger. And one more point is probably also to think about that these correlations not only affect the quasi-particle masses, but also affect the sizes of the Fermi surfaces. So as we increase X, we increase the bandwidth, and we are likely to reduce the strength of this correlation. And this is why also the Fermi surfaces keep increasing as we increase X, both in the series iron selenium sulfur and also in the barium-122 system. So what can cause the suppression of the critical fluctuations in iron selenium sulfur system? So one potential reason for the suppression could be the interaction with the lattice. And in this theoretical work, has been suggested that if there is a strong interaction with the acoustic phonons, there will be only two critical directions, and the rest of the system all the critical fluctuations will be suppressed. And the phase diagram for such a system will have temperature versus coupling parameter between the electronic system and the lattice. Then we expect that in the presence of this coupling, the whole phase diagram to be shifted to a different location. So in reality, the real critical point will be somewhere inside the nematic phase. At the same time, the transfer properties are expected to be non-Fermi liquid behavior and then to cross over to Fermi liquid at low temperatures. And here from the resistivity data under pressure, we detect the Fermi liquid temperature of about 13 Kelvin in this case. And this allows us to estimate what will be this potential coupling parameter between the electronic system and the lattice. And these are the values that we get, about 0.07 in this case. And very recently, this approach has been also applied to Raman studies. And what Raman study says, it also can detect nematic susceptibility. And from the intercept of the Curie-Weiss temperature, they suggest that this intercept shifts to a different value, and they propose that nematic elastic coupling shifts the position of the nematic critical point in the system due to this finite interaction. They also suggest that the itinerant and more localized type of carriers could also be responsible for the Raman spectrum because they separate the system into components. Interestingly, they are able to detect the values of the scattering parameter and suggest the sulfur iron selenium system has a much stronger coupling compared with our other system like barium-122. We know that the systems are extremely soft, so we should expect that they will be prone to these effects. Now, if we have this coupling with the lattice, then we potentially will be affected also in the transport behavior. And theoretical studies by Rafael Fernandez group show that the resistivity coefficient, which is here alpha versus the Fermi energy and versus temperature, temperature scale. Here, as we cool down to low temperature, this exponent could vary from a value of 1.3 towards 2. And as a function of the coupling with the lattice, these exponents will change significantly and they have very strong temperature dependence. And if we look at our data under pressure, we extracted the exponent, and this exponent requires a very careful understanding of the low temperature residual resistivity, which can be extracted from high field data. We see that our exponent sits nicely around 3.2, close to the critical pressure, and afterwards a low temperature, the system moves towards the Fermi liquid behavior with n equals 2. And we can plot the data in different way by plotting directly resistivity versus 3/2. So these are composition in the vicinity of the nematic endpoint, a high temperature. And we can see that over a very, very large temperature regime, this dependence seems to hold. The same for the pressure dependence in the vicinity of the nematic endpoint. We have a very nice 3/2 dependence. As I mentioned earlier, the theory suggests that no non-Fermi liquid behavior will occur in a regime outside this nematic endpoint, and eventually the system will show Fermi liquid behavior, and this is what we see in our experiments. And a few more points just to finish off is about the role of spin fluctuations. So far we were searching for nematic fluctuations and to see what role they play in superconductivity. But in iron, selenium, sulfur, we know that spin fluctuations are likely to be responsible for superconductivity. And here, this NMR study shows they are likely to be enhanced inside the nematic phase around 10%. And as compared to what we heard before from Naja's talk, we do identify linearity behavior for most of the samples inside the nematic phase. And even the 17% sample he referred to is just on the border. So it's every time we are inside a nematic phase, there is a regime where a linear T behavior can be found over a limited temperature regime. Eventually, all the materials will become Fermi liquids, and we see quantum oscillations in all these concentrations. So now thinking about superconductivity, so we learned that in the presence of the coupling with the lattice, the superconductivity is unlikely to be enhanced at the nematic critical point, as initially suggested by theory, which do not consider the effect of the lattice. But also in this particular material, it's probably also is telling us that the pairing might have not been influenced by nematic fluctuations at all. So if the spin fluctuations are responsible, then we expect that when the spin fluctuations are strong, like inside the nematic phase, then we will see an enhancement in superconductivity, which is what experiments show. A very small dome exists inside, but not at the nematic endpoint. And this is my summary. So quantum oscillations gave access to the Fermi surfaces and also to the quasi-particle masses. And in particular, we can follow very well the behavior of the hole bands as a function of chemical pressure and applied pressure, and search for evidence of divergent fluctuations in the vicinity of the nematic endpoint. We could not find any divergence. We can see smooth variation of quasi-particle effective mass in both cases, suggesting that either that this type of fluctuations are possibly quenched by the interaction with the lattice. And from the transport point of view, inside the nematic phase, things are indeed very complex, but just outside, we find a region where resistivity follow a 3/2 power law, and linearity behavior is in the vicinity inside the nematic phase over a limited regime. And again, we believe that this linear T is likely to be associated with spin fluctuation, which has been assigned also in other systems. Thank you.
Thank you, Amalia, for this beautiful talk. So just a very quick comment. I think this large nematoelastic coupling that shift the quantum critical points in the iron selenide system is quite interesting. So in Wednesday, I think Matthias Ikeda, he will be talking about his recent elastochloric measurements, and then showing that in the cobalt-barium 122, the iron nictide system, the nematoelastic coupling actually vanishes near the quantum critical point. So that's a very interesting contrast. And then my group also has some independent measurements showing the same effect. So, okay, let's have one or two quick questions. So I have Peng Chen raising hands.
Yeah, okay. Yeah, thanks, Amalia, for the very nice talk. Yeah, so I have two questions. The first question is concerning the quantum oscillation. So does tuning have any role to play? I mean, in terms of measuring the quantum oscillation from the underdope side to the pure, overdope side with a phosphor? Because in the pure overdope side, it's tetragonal throughout, right? Whereas in the underdope side, the system actually have a tetragonal orthorhombic phase transition. So that's one question, number one. Let me ask both questions, then I'll just wait for answers. So the other question I have is that you said that the lattice coupling plays an important role in determining the differences between the phosphorus and the sulfur dope samples. But in the case of a phosphorus dope samples, I mean, the transition is always first order, right? You have a coupled structural and magnetic phase transition. Whereas in the case of the sulfur dope iron selenide, you only have the structural phase transition. So how do you, I mean, they both couple to the lattice somehow, right? How do you tell the differences between the two? Yeah, that's my two questions. Yeah, thank you.
So I think the first question was about when we determine quantum oscillations, if we think about
does tuning play a role?
If the tuning parameter plays a role.
Right. I mean, I was just curious. The system.
Okay, so I think we have to think about what quantum oscillation measures. Actually, we measure areas. Okay, so if we think about what we probe, we measure cross-section areas. If that area is slightly distorted, or if it's completely isotropic, it's still an area. And especially in the vicinity of the nematic endpoint, we know from ARPAs that these areas become more and more isotropic. So in a way, because quantum oscillation probes area is not affected by other parameters. In a way, we measure an area. So it's the cross-section area of a Fermi surface and the quasi-particle cyclotron average quantity for that particular pocket.
So you don't think the green boundary scattering from the different domains plays a role?
So the quantum oscillations are only observed if we do not make them incoherent in a way. So they need to have a particular phase. If we start scattering, they will be completely damped. So that's the beauty of quantum oscillations. We can really access, because the samples are very clean, we can really access the Fermi surface directly.
Okay.
About the
second question, yeah.
The nematoelastic coupling, obviously, what I'm proposing here is a way to try to understand why these nematic fluctuations are quenched. I mean, one possibility, as I said, is this criticalities, even from theory, is expected only to occur along certain direction. Only two direction will be critical. What we measure here is an average effect. So the question is it because we average out all the effects, or is it because this it's a real effect and this nematic elastic coupling kills all these fluctuations? But because TC is also suppressed, we know things are more severe. That means these critical fluctuations are really somehow quenched.
Okay, yeah, thank you.
One more question from Qin Miao.
Thank you. Really nice talk about it. So I just want to take advantage of the fact that both you and Nigel are here and see whether I understand where you agree, namely at the critical concentration, X equal to 0.17 ambient pressure, you both agree that there's a T-linear resistivity from say 25 or 30 Kelvin down to say 2 Kelvin. Is that a fair representation so in other words, over a decade of temperature, there is T-linear resistivity?
So I think probably what we agree, well, I'll speak for myself first, and then I'll let Nigel agree or disagree with me. So the linearity resistivity Nigel is talking about is called 0.16, but 0.16 has a TS of 50 Kelvin. So that means 0.16, what is nominal composition and corresponds to a TC sample of 50 Kelvin. So if we go to the phase diagram, then 50 Kelvin is somewhere here, And that's inside the nematic phase where we also see linearity. So from the data point of view, both our data agree that inside the nematic phase, there's a linearity.
Yeah, that's fine. I mean, I even don't, for theorists, 0.16 and 0.17, I probably would not, cannot tell, at least for me. But what the point I want to make is that to the extent that is the case, if I define the A coefficient of AT squared over that temperature range, then that A coefficient is very large. So I'm somewhat confused as to why there is T linear resistivity at that particular concentration, and yet the A coefficient is being described as very small or not large compared to the paramagnetic case.
We have data all the way to 0.3 Kelvin. So I think probably what's worth, I mean, these are difficult experiments to get all the way to low temperature and to suppress the magnetoresistance. You have to be in play to do longitudinal magnetoresistance studies in about 45 Tesla or higher. But I can give you another example. Look at the 4%, okay? This is very deep inside the nematic phase. And if you look at this data, you will say, well, this is linear T, okay? But we see very beautiful quantum oscillation. And if you zoom in within this regime, eventually is a T square dependent.
I understand. So the point is that when one makes a statement about what the mass is or what the A coefficient is, one has to specify for which temperature range that statement is being made. Is that a fair?
Yes, I think we are talking about within the lowest possible temperature, below 1.5. So our data are between 0.3 to 1.5. This is the kind of almost the ground state.
Because in principle, I could take the point of view that maybe at the lowest temperatures, a lot of things happen, coupling to the lattice. You know, in heavy fermion physics, we even see coupling to nuclear spins, etc. But there's enough of a dynamical range of, say, a decade or more, in this case, 30 Kelvin to 2 Kelvin, where things are more universal, like there's linear resistivity or A coefficient as defined in this temperature range is enhanced. And I wonder, for instance, RPES, maybe either XY band or XZ band would actually pick up some mass enhancement over that temperature range. I don't know whether that is the case, but I just want to raise that as a possibility to think about, and maybe there's the details that can be probed.
So,
well, okay, Nigel.
No, I mean, no, I think the data agree pretty well. I think the thing that, you know, you see from this plot, so at 25%, yeah, we see T squared below around 10, 12 Kelvin. Amalia sees it below 9 Kelvin with a very similar coefficient. Around 18%, we see T squared below around 5 Kelvin. It's hard, I think, to claim it's 2 Kelvin there, Amalia, with the number of data points you have, but it's similar. But the coefficient itself is enhanced by about a factor of 3 as you get to 0.18. And then at 17%, the data I showed you does go down linearly down to about 1.5K. And as Chi-Mao says, you know, if it does cross over eventually to T squared, it does have to have a very large A coefficient. So as you approach from the 25% towards the critical point, there is a reduction in the regime over which the T linear behavior is shown, and you plot that in your measurement. And then there's also, you know, there has to be a significant enhancement in that regime. I think inside the nematic phase, it's more complicated, but certainly on the outside phase, which is where we say comparing it with the barium 122, there is a similar behavior.
So I think probably it's worth also looking to all the possible parameters you can measure. And here there's also specific heat, gamma coefficient. And again, there is not really any enhancement.
No, but I'm talking about, you know, as the approach towards, you know, this XC from the tetragonal side, where you can imagine the system being increasingly dressed by fluctuations associated with some order.
Yes, I mean, indeed, one can see that if we look at this graph, if we represent it over a bigger scale, because in the barium 122 system, we have to remember we started from the tetragonal towards the spin density wave. So when you move from here, you change the mass from about 2 to about 3.5. So that's what criticality and the values we were talking about in the barium 122 system. That's the enhancement. Here, if we look at the tetragonal phase end member, you can see again, this mass is much lower, is just below 3, and then it goes all the way to 5. So there is mass enhancement as we approach the nematic phase. But as you can see, that enhancement seems to peak inside. So this is where the spin fluctuation seems to be the most enhanced. So that just probably points out that spin fluctuations
I agree with what you're saying, Amalia. And the data, I'm not disputing your data. I'm just referring to Chimal's question that I don't think there is any significant difference in the data in terms of how the resistivity evolves as you approach it from that side. That's all. And that, it is a puzzle. I accept it's a puzzle why this coefficient grows much more rapidly than the M star. And there's clearly some interesting decoupling here from the usual Karawaki-Wood scaling. That's all.
So I think we have an excellent topic for the open discussions, and hope you two can still join at that point. And we're very behind the schedules, but it's good because we have a lot of exciting discussions and then beautiful talks.